In Chapter 4, we're considering different types of reactions. One such type is called an oxidation-reduction reaction. An important initial step to understanding oxidation-reduction reactions is to be able to assign oxidation numbers. And that's the focus of this particular video. There are different types of reactions discussed in Chapter 4. If we're looking at redox reactions, the first thing that we need to do is be able to assign oxidation numbers. In terms of the learning objectives for this chapter, most students do well in terms of assigning oxidation numbers. Somewhat more difficult is interpreting redox reactions, and much more difficult interpreting the activity series, but it all begins with having a strong understanding of oxidation numbers. An oxidation-reduction reaction. The reaction of calcium solid with oxygen gas to form calcium oxide is an oxidation-reduction reaction. We have a transfer of electrons. We have a substance losing electrons being oxidized and a substance gaining electrons being reduced. That's what's being shown in this part of the picture, where they show electrons being transferred from the solid to the gas. To determine which substance is oxidized and which one's reduced, we must first assign oxidation numbers. Here's a typical question involving assigning oxidation numbers. Determine the oxidation number of sulfur in each of these following substances. This question suggests that the oxidation number of sulfur can change. So our approach for determining oxidation numbers must account for this fact. We're going to need to memorize some information, but we're also going to have to use problem solving. We must do more than simply memorize. We're not going to memorize the oxidation number of every atom in every substance. We need a plan. Here's a description of oxidation numbers in the textbook. The overview is the same point that I was trying to make. Before we can identify an oxidation-reduction reaction, we need to have a bookkeeping system, a way of keeping track of electrons that are gained by the substance being reduced and electrons being lost by the substance being oxidized. That's what oxidation numbers are used for. Second thing to point out is we assign oxidation numbers for every atom. We don't have oxidation numbers for a particular compound. We can assign oxidation numbers for every single atom that we find within the reaction. There's various rules that we follow that gives us a plan for determining oxidation numbers. Here's the first one. For an atom in its elemental form, the oxidation number is always 0. For each hydrogen atom in H2 molecule, each of the hydrogen atoms has an oxidation number of 0. Same thing for the phosphorus atoms in the P4 molecule. The only time an atom has an oxidation number equal to 0 is when it is in its elemental form. So consider these various substances. Atoms in which of these substances have an oxidation number of 0? And also, give your own example of a substance in which the atom's oxidation number is 0. Pause the video, give that a try. Second rule. For any monatomic ion, the oxidation number equals the ionic charge. There's a description how the alkalis would have a charge of +1, the alkaline earth +2. Goes on to describe how aluminum would be +3, sulfur would be -2. That's consistent with how we've been using the periodic table thus far. But let's be careful here. This is describing examples when we have ionic compounds and we're looking at monatomic ions. Lithium is the cation all by itself. Sulfur is the sulfide anion all by itself. So with this guideline, determine the oxidation of sulfur in each of the following substances. That's our initial question. Based on rule number 2, which cases now can we assign the oxidation number for sulfur, and what is the oxidation number? Pause the video, give that a try. Rule number 3. Nonmetals usually have negative oxidation numbers, although they can sometimes be positive. Couple thoughts on this one. So nonmetals include hydrogen, and then our grouping here on the right-hand side of the periodic table. I'm not worrying about noble gases because they're not going to be found in compounds that we're going to be interested in at this time. This description, nonmetals usually have negative oxidation numbers, although they can sometimes be positive. It's describing some variability. It's not as clear as in our earlier examples, so we have to be a little bit more careful and understand what this is saying. Let's step through the points. First of all, the oxidation number of fluorine is -1 in all compounds. Okay, that's great. So within our problem solving, as soon as we see fluorine in a compound, it's going to be -1. Fluoride is always -1. The only time it wouldn't would be in F2, the elemental form for fluorine. The other halogens are going to be usually -1, although there might be exceptions. But typically, we'll see that column be -1. Next group, oxidation number of oxygen, -2. That would be the column that I would be placing it in. That's true in both ionic and molecular compounds. However, we do have a particular exception. I think of oxygen as always being -2 unless it can't be. I'll show you an example where that's the case. But in general, if you view oxygen as -2 and have that fixed within your problem solving, you'll be on the right path. Hydrogen's a nonmetal. Recall it can be +1 or -1 for its common charges. We have a description here. +1 when bonded to nonmetals and -1 when bonded to metals. An example would be the sodium hydride. So with hydrogen, we have to be careful as well, but I think we have a good framework for describing its oxidation number. Okay, here's 4 examples. I tried to pick a variety that would be illustrating different ideas for these nonmetals. What I'd like you to do is assign oxidation numbers for the hydrogen atoms in each of these compounds. Pause the video, give that a try. Our last rule, the sum of the oxidation numbers of all the atoms for a neutral compound adds up to 0, and the sum of the oxidation numbers for a polyatomic ion equals the overall charge of the ion. The second portion of that is especially important for us. The sum of the oxidation numbers in a polyatomic ion equals the charge of the ion. That's another reason why it's really important for us to memorize our polyatomic ions and what their overall charge is. Example exercise 4.8 steps through different examples. If I double back for a second, it's leading us to this and pointing out that within our problem solving, sometimes you have to go back and forth. You have to see which parts you know for certain and use that within your problem solving to find the remaining portion. I'm going to illustrate that as we step through how sample exercise 4.8 is solved. So what I'd like you to do is, first of all, give it a try. Determine the oxidation of sulfur in each of these examples, and then we'll step through to see how the book describes how to answer them. I'm putting a periodic table on the screen just to remind you that if your task is to determine oxidation numbers, many times looking to the periodic table is a helpful first step. Give each of these a try, and then we'll step through the answers. Here's the solutions. So for the first one, H2S, I would say that sulfur is in my -2 column. How do I deal with hydrogen? I would say in this case, hydrogen is bonded to a nonmetal. So it has each hydrogen has an oxidation number of +1. The sulfur is -2, so the entire molecule is neutral. S8, that's the elemental form of sulfur. It's a cool thing if you want to memorize it, or you could recognize that sulfur, it's the only element there. It's only sulfur being found in the substance. It's only sulfur 8 molecules, so it's going to have an oxidation number of 0. An example where sulfur is being found in a binary compound, I would begin my analysis here by saying I think I know what the Cl is going to have for an oxidation number, -1. I have 2 of those, so the sulfur is going to be +2. Back and forth looking at this ionic compound. Well, I know that each sodium is going to be +1, so that gives me a total of +2. Then I'm going to jump over to the oxygen. Oxygen, as I mentioned, is almost always going to be -2, so we can see how many of those we have. And then the remaining one, the last one to find, would be the oxidation number for the sulfur itself. So my problem solving, I'm going back and forth and leaving that for last. And then finally, for the sulfate anion. Oxygen again, -2. The overall charge is -2, so I have 4 oxygen atoms, each at -2. The overall charge is 2-, so the final thing that I would solve for would be the sulfur itself. So take a second, either based on how you did, what you learned along the way, which of these questions do you think would you predict would score the lowest on the exam? Which of these is the most difficult and why? Pause the video, share your view. To finish with, this is the question that we opened with. Determine the oxidation of sulfur in each of these substances. Give that a try. This reinforces some of the ideas that have been talking about. See if you get stuck on any ones, share your ideas, and we'll see if we can't get through it.